Yes? All right, so let's go ahead and do this. I'm going to have the outer integral. I didn't put my limits of integration. I need to do that. What's going to go on the inner integral? 1, 2, and outer 0 pi, right? So I have 0 pi here. Let's go ahead and see if we can't find the antiderivative. I'm nervous about what I'm going to get for answers here. What's the antiderivative of y sine x y with respect to x? Cosine negative cosine xy over y. That's it. That's it right there.
Oh yeah, it cancels out. That's right.
Look, if you get hung up on this, here's what I recommend you do. Okay, if you actually are hung up on this, just replace y with a number, okay? 2 sine of 2x. Integrate that. So the 2 can come out, right? Dx in there, sorry. I just have to trust you're in Cal 3 that you can integrate sine 2x. Antiderivative of sine of something is negative cosine, but then you have to scale out 1/2. That 1/2 comes out and pops that 2, and it's gone. So this is it right here. And then what? 1 and 2, right? That's it, like that. And x, right? This time we're going x. All right. Let's proceed. Continuing there, this is going to turn into integral 0 to pi. All right. Plug in 2 for x. You get negative cosine of 2y, right? And then plug in 1 for x, and you get minus and then negative cosine of y dy. Do you all agree with me on that? This is just a plus, isn't it? Now you can integrate with respect to y. So what is the antiderivative of negative cosine 2y? Negative 1/2 sine 2y. You're going to have to probably brush up a little bit on your integration. I know it's been a while. Here, sine y. From y 0 to pi. Okay, here we go. Let's plug in pi. 2 pi. Sine of 2 pi is 0. That's gone. Sine of pi, 0. So we get 0 minus, now plug in 0. 0 again, everything's 0. All that for nothing, right? The volume is 0. Okay. Maybe we should take a look at it. Are there any questions over the integration, though? What do you notice here on this one that's different than the last one? Part of the function is above, the surface is above, and part of the surface goes below the xy plane. So guess what? It's counting the part below as a negative volume. It's counting the part above as a positive volume. We saw this in Cal 2. We saw the same exact thing. If you had a polynomial function, or any function, let's take the sine function. If you were in Cal 1 and you integrated the sine function from 0 to 2 pi, your answer is 0. You can check it yourself. And it's because back then it counted that as positive area and it counted this down here as negative area, and they wiped each other out. So the way that you could get around that is you could figure out where it hits the x-axis, couldn't you? And just integrate from here to here, and then you could like double the answer, couldn't you? Is that going to be easy for us to do here, though? No. Because we would actually have to figure out where this surface hits the xy plane. So we would actually have to solve, what was it, y sine xy? We'd have to set that equal to 0. And we'd have to find all solutions that live in that domain. And it's going to be a curve. And that we're not even going to touch that. We're not even going to mess with that. Right? But I'm just showing you that it inherently has some more difficulties than you do back in Cal 1 or Cal 2. God, I keep on saying Cal 2. Cal 1. All right. Fubini's theorem. So remember I said we had some choices on the order of integration? This theorem verifies that. But there is some stuff that we need. Your function must be continuous, which means that your surface must behave pretty well. As long as it's continuous over the rectangle, the order of integration doesn't matter. On a rectangle, it doesn't matter. Verify. I don't think I'll verify this. What you can do on your own, though, is just try this. Try setting this up both ways. Right? Set it up both ways. This one, what would be the limits on the outer one here? 1, 2, and here 0, 1. This one the other way around. You do this on your own. Show that those are equal. You'll get the same answer both ways. And it's because this function is well behaved. Xy squared is a nice continuous function. The order of integration shouldn't make that much of a difference in the antiderivative here, should it? No? Seems like both ways would be okay? Now we do have a special case. If the function of two variables that you're looking at can be rewritten as the product of two distinct functions, one of them being a function of x, the other one being a function of y, then you can do something you've never been able to do before. And that's split a product inside of an integral into a product of two separate integrals. You've never been able to do this, ever. You can only do it if the function of two variables can be split up into two functions. You'll see, let me show you an example of how this would work. Right here, this one. So find the volume under sine x cosine y on the following rectangular region. So when you look at this, can you see right here, this is a function of x, and this right here is a function of y, and they're separated by multiplication. They are distinct. They're separated. Yes? Compare that to the one we did earlier. We did a double integral as this one. Right? This one wouldn't work, would it? Because this sine function has x times y inside of it. I would need this just to be x. Then I could split it into two, because that would be a function of y. This would be a function of x. So this would not fall into the special case, but that one does. So here's what I can do. I can take this double integral over the rectangular region of this function with respect to its area, and I can rewrite it as two integrals, one with respect to x, one with respect to y, and I can multiply the two answers. Now, the one with respect to x is just sine x. And what are my limits of integration on x? 0 to pi over 2. And over here is the distinct function of y, which was cosine y. And my restrictions here are 0 to pi over 2. That's only because these were separated, right?
So if we could write a function like that, say, we could factor it to the point that looks like we could separate it. That's also
Yes.
we can do that.
Yes. Now, I'll be honest with you. We don't use this much. But when it does creep its little head out, you want to pop and get on it as soon as you can, because it saves you time and energy if you can do that. Right? Because these two are pretty clear, pretty clean? Okay. All right, so should I keep going or no? You can do that? You can do that? Okay. Dot, dot, dot. All right, a couple of properties of double integrals. These are going to seem very similar to things you saw with regular integrals back in Cal 2. If you have the sum or difference of two different functions of x and y, you can split it up into two different double integrals, as long as it's plus or minus. If you have a constant in front of a function of two variables, you can pull the constant out. That we did before. If you have a function that's bigger than or equal to another function for all x's and y's in the rectangular region, then the volume under this one should be greater or equal to the volume under this one. So that's just saying if I have a surface that's above another surface, then the volume under this one has to be bigger than or equal to the volume under this one. Now let's see if you can recall this again from Cal 2. When you first went to Cal 2, they said, hey, here's the area underneath some function f, right? They say, hey, the integral, and there's the area. Then after that, they said, well, what if you had another function, g, and you wanted to find the area between them? Then you just subtract, right? You take the area under f, you subtract the area under g. So back in Cal 1, this turned into a, b, f minus g dx, right? That would represent the area in between. We have the exact same thing for the volume between two surfaces. If you're given two surfaces, f of x, y, and g of x, y, on some rectangular region, then the volume between them is the difference between the functions. But because of properties of double integrals, I can split it into two separate ones, right? So it's just here's the volume under f, subtract the volume under g. That'll be the difference in the volumes. Now this is assuming here that f was bigger than g. If g was bigger than f, then you would get a negative volume as an answer. Here's the picture of that. I think this is a pretty good picture. You've got the domain on the ground. You've got surface g, which is below surface f. And so you're trying to find the volume between those two. All right. We actually covered a little more ground than I thought we were. There's the homework. That's it for 12.1. Rectangular regions are the cleanest, easiest things you can do with double integrals. So where we're headed now is, okay, what if you don't have a rectangle? I'm leading into next class. What if instead of having a nice pretty rectangle here, I say, all right, still keep your x's between these two constants. So it's almost like a rectangle here. But on this way, on the y's, how about you just like fix it between two functions? So now you're looking, it's almost like a half rectangle. Like this is fixed, A and B, right? Your x is between two constants, but your y values are no longer between two constants, right? They vary. So this is a function of x, isn't it? This is a function of x. This is what we're going to refer to next class as a type 1 region. Your x's are between two constants, right? But your y's are between what? Two functions of x. So some function of x here and some function of x here. So this will be like f and this will be g. How do you think that changes your double integral? Well,
instead of plugging in constants, you plug in.
yeah, see, what's going to change here is you can no longer dictate the order of integration. You can't just swap around. Here you're forced to do your x's last because they're constants. So you have to do ab, dx on the outside, which means dy goes here. And then guess what? Your limits of integration are not numbers anymore. They are actual functions. So you're going to have g of x here, and f, I think we're going to use g and h, not f. So whatever this is here, you're going to find the antiderivative with respect to y, whatever that is. But instead of letting y be 2 and y be whatever, you're going to let y be whatever that is. And let y be whatever, and plug it in and subtract. So you're going to be plugging in functions instead of constants. It's just going to get nastier, but it's not necessarily any more difficult. And then what we do is we just rotate this around, and we do it the other way. C, D, and we have a type 2 region, which now your y's are between two constants, right? And your x's are between two functions of y. And so this changes C to D, functions of y, D switch. But that's all next class. All right? And after that, what do we do? Luckily, there will only be those two types. Then what we're going to have to do is we're going to have to change. Look, I still have 3 minutes. Hold on. So what's going to happen after? I'm just trying to lead you into where we're headed, okay? So you just get the big picture. What we're going to do is we're going to say, well, what if you have a region that looks like this? I mean, that seems like a natural region to want to integrate over. Circle or something like that. See, that's not a type 1 or type 2, because you can't fix your x's between two constants and your y between two functions, because the top part of a circle and the bottom of a circle are not a function. So what we're going to do in order to attack this, we have to change our whole perception of coordinate systems. So what we're going to do is go to polar coordinates to do this. We're going to get out of Cartesian coordinates and go to polar coordinates. If you've never seen polar coordinates, it's okay, because I'll treat it like you've never seen it. But it'll be a quick, hey, these are polar coordinates, now let's get moving. All right? So we do polar coordinates. And then we pretty much can handle almost every type of region. Not all of them, but that takes care of a lot. Then from there, we go to triple integrals. So for triple integrals, your domain now lives where? Because for a double integral, the domain was in two-dimensional space. For a triple integral, your domain is actually three-dimensional space. So we start with the easiest three-dimensional solid you can think of, a box. So you know how we integrated over a rectangle to start here? When we get to triple integrals, the first one we'll do is integrate over a rectangular cube-looking thing. And then you start doing something like that in three-dimensional space. It gets very complicated, because you can actually have like 6 types, type 1, 2, 3, 4, 5, 6. There's a bunch of different types. So. And then we realize, you know what, that Cartesian's not good enough, so we use spherical coordinates and cylindrical coordinates to do those. So we're going to, by the end of like the next few weeks, we will have introduced ourselves to polar coordinates, which is a way of representing two-dimensional space, alternative to Cartesian. We will go to cylindrical and spherical coordinates. So we're going to have at least 3 new coordinate systems that we're going to be working with in here. All right. Now I'm out of time. Y'all have a good day. Yes?
Mini exam 5 due next class?
I think the mini exam 5 is due next class. Yeah, Wednesday. Yeah, you should be able to do everything on it. I thought for sure that's what you did.